Chapter 9 Scheduling and Proportional Share. In this chapter, we will examine a different type of scheduler known as a proportional share scheduler, known as sometimes referred to a fair share scheduler. Proportional share is based on around the simplest concept. Instead of optimizing the turnaround or response time, a scheduler might instead of try to guarantee that each job obtained in a certain percentage of CPU time. An excellently uh, early example of a proportional share scheduling is found in the research by the Waldspurger and Weil and is known as lottery scheduling. However, the idea is certainly older. The basic idea is quite simple. Every so often, hold a lottery to the determining which process should get run next. So processes that should run more often use the given more chances to win the lottery. Easy? No. Now on to the details. But now before our clocks. The clocks, how to share the GPU proportionally. How can we design a scheduler to share the CPU in a proportionally manner? What are the key mechanisms for doing so? How effective are they? Section 9.1 Basic concept. The ticket to represent your share. Underlying the lottery, the scheduling is one very basic concept. Tickets, which are used to represent the share of the resource that a process or users or whatever should receive. The percent of tickets that are processed has represented each sharing of the system resource in question. Look at the example. Imagine the two processes A and B, and further A has 75 tickets while the B has only 25. Thus, what we would like to be A to receive the 75% of the CPU and B remaining of the 25%. Load scheduling achieved this probabilistically, but not deterministically, by the holding a lottery every so often, say every time twice. The holding a lottery is straightforward. The scheduler must know how many total uh, tickets there are. In our example, there are 100. The scheduler then picks a winning ticket, which is a number from 0 to 99, and assuming a hold ticket 0 through the 74 and B 75 through a 99. In the winning tickets simply determine whether A or B runs. The scheduler then loads the state of that winning process and runs it. So here, the randomness, one of the most beautiful aspect of the lottery schedule is the use of randomness. When you have to make a decision, the randomized approach is often a robust and a simple way to doing so. Random approaches have at least three advantages over more traditional decisions. First, random often avoid strange corner case behavior that more traditional algorithm may have trouble handling. For example, consider the LRU replacement policy studied in more detail in the future chapter on virtual memory. While often a good replacement algorithm, LRU attain a worst case performance for some cyclic sequential workloads, so the random, on the other hand, has no such worst case. Second, a random also is the right way and requiring little state to track alternatives. In a traditional fair share scheduling algorithm, tracking how much CPU each process had received requires per-process accounting, which must be updated after running each process. Doing so randomly necessitates only most minimal of the per process data easy for the number of the tickets each has. But finally, the random can be fast as long as generating a random number is quick as making the decision is also thus Random can be used in a number of places where speed is required. Of course, the faster the need, the more random tends towards the pseudo-random. So, here an example output of a lottery scheduler winning tickets. Here is the resulting schedule. As you can see from the example, the use of a random list in a lottery scheduling leads to a probabilistic correctness in meeting in the desired proportion, but no guarantee. In our example above, we only get to run 4 of the 20 time slices, 20%, instead of the desired 25 allocation. However, the longer these two compete, the more likely they are to achieve their desired percentages. Tip: the use ticket to represent shares. One of the most powerful and basic mechanisms to the design of the lottery and stride scheduling is that the ticket is used to represent a process shares of the CPU, and this example you can be applied much more broadly. For example, in more recent work on virtual memory management for the hypervisors. Wardswonger showed how tickets can be used to represent the guest operating system share of the memory. Thus, if you are ever in need of a mechanism to represent a proportion of ownership, this concept just might be, wait for it, the ticket. Section 9.2 Ticket Mechanisms. Lottery scheduling also provides a number of the mechanisms to manipulate tickets in different of the sometimes used way. One way is the concept of the ticket currency. Currency allows the user with a set of the ticket to allocate the tickets among their own jobs in whatever currency they would like. The system then automatically converts that currency into a correct global value. For example, assume users A and B have each band given 100 tickets. A user running 2 jobs A and B and give them each 500 tickets of the 1000 total in A's currency. User B is running only 1 job and gives in 10 tickets out of 10 total. The system converts A1's and A2's allocation from the 500 each in an A's currency to a 50 each in the global currency. Similarly, B1's 10 tickets is converted to 100 tickets. The lottery is banded hold the global ticket currency to 100 total to determine which jobs runs. Another useful mechanism is to ticket transfer. With a transfer, a processor can temporarily hand off each ticket to another process. This ability is especially useful in a client-server setting where a client process sends a message to a server asking it to do some work on client behalf. To speed up the work, the client can pass the ticket to the server, thus try to maximize the performance of the server while the server is handling the client request. When finished, the server then transfers the ticket back to the client and all is as before. Finally, ticket inflation can sometimes be a useful technique. With inflation, a process can temporarily raise or lower the number of the tickets it owns. Of course, in a competitive scenario with processes that do not trust one another, this makes little sense, and when greedy process could give itself a vast number of the tickets and take over the machine. Rather, the inflation can be applied to an environment where a group of processes trust one another. In such a case, if any one process knows it needs more CPU time, it can boost each ticket value as a way to reflect the need to the system, or without communicating with any other processes. Figure 9.1 Lottery Scheduling Decision Code. Figure 9.3 Implementation. Probably the most amazing things about lottery scheduling are the simplicity of its implementation. All you need is a good random number generated to pick up the meaning bit as a data structure to track the purposes of the system, for example, a list, and the total number of the tickets. Let's assume we keep the processing list. Here is an example comprised of the 3 processes A, B, and C. each with some number of tickets. To make the scheduling decision, we first have to pick the random number as a winner from the total number of the ticket 400. Let's just say we pick the number 300, and then we simply traverse the list with a simpler counter to use to help us to find the winner, figure 9.1. The code of the works of the list of the processes, adding each ticket value to the counter until the value exceeds the winner. Once that is the case, the current listed element is the winner. With our example, the winning of the ticket being 300, the following take place. First, the counter is implemented to 100 to account for the eighth ticket because 100 is less than 300. The loop continued. The line counter would be updated to 150 this ticket. Still less than 300 and thus again as we continue. Finally, the counter is updated to 100, clearly greater than 300. And thus we break out the loop with the current pointing at C for the winner. Figure 9.2. The lottery fairness study. To make the process most efficient, it might generally be the best of the organized the listing sorted order from the highest number of the ticket to the lowest. The ordering does not affect the correctness of the algorithm. However, it does ensure that in general the fewest number of each list the iteration are taken, especially if there are few processes that possess the most of the tickets. 9.4 an example. To make a dynamic of a lottery scheduling more and understanding that we now perform the brief study of the completion time of the two jobs competing against one another, each with the same the number of the tickets 100, as same the long time, r which we will vary. In this scenario, we'd like for each job to finish roughly at the same time, but due to the randomness of the lottery scheduling, sometimes one job finishes before the other. To quantify the difference, we define a simple fairness metric. F which is simply the time the first job completed divided by the time the second job is complete. For example, if R is 10 equals 10 and the first job finished at time 10 and the second job is at 20, F equals 10 over 20, 0.5 when both jobs finish at nearly the same time. F will be quite as close to 1 in this scenario. That is our goal. A perfectly fair schedule would achieve the F equals 1. Figure 9.2 plots the average fairness of the length of the two jobs R is varied from 1 to 1000 over 30 trials. These are generated divided similar to provided at the end of the chapter. As you can see from the graph, as when the job length is not very long, the average fairness can be quite low as only as jobs run after a significant number of time slices does the lottery scheduler approaches the desired fair outcome. 9.5 How to assign tickets. The one problem we have addressed with lottery scheduling is how to assign a ticket to job. This problem is a tough one, and because of the course, how the system behaves is stronger dependent on how tickets are allocated. One approach is assume that users know the best. In such a case, each user is handed some number of tickets, and a user can allocate tickets as many jobs as desired. However, this solution is a non-solution and rarely does tell you what to do. Thus, given a set of sets, the ticket presentation problem remains open. 9.6 is the sliding scheduling. You might also be wondering why use randomness at all. As we saw above, while the randomness gets a simple and approximately correct, scheduler is occasionally will not deliver the right proportion, especially the over short time scale. For this reason, Ward Spongers invented stride scheduling. a deterministic fair share scheduler. Stride scheduling is also straightforward. Each job in the system has a stride, which is inverse in proportion to the number of tickets it has. In our example above, with the jobs A and B and C with 150 and 25 tickets respectively, we can compute the stride of each of them by dividing some large number of the tickets such each process has been assigned. For example, if we divided 10,000 by each of those ticket values, we obtain the following stride of the value of for A, B, and C, and 100, 200 for Li. We call this value the stride of each process. Every time the process runs, we will increment the counter for it. It calls as a path value by each stride to track each global progress. The scheduler then uses the stride and path to determine which process should next run. The basic idea is simple. At any given time, pick the process to run that has the lowest path value so far. When you run a process, increment each path and counter by each stride. A pseudocode implementation is provided by the Warsprunger. As in our example, we start with the three processes A and B and C with stride values of 100, 200, and 40, and all with the path values initially at 0. Thus, at first, any of the processes might run as their path values are equally low, and assume we pick A arbitrarily. Any of the processes with equal as now low path values can be chosen. Runs when finished with the time slices when update its path value to 100. Then we learn a B whose path value is then set to 200. Finally, we run C whose path value is incremented to 40. As at this point, the algorithm will pick the lowest path value, which is 6, and run it and updating its value to 80. This stride is 40, as you recall. As then the C will again as still the lowest path value, raising its path to 120. We will now updating its path to 200, now equal to this, and C will run twice more, updating to passes 160 and 200. At this point, all path values at equal again, and the process will repeat an infinitum. Figure 9.3 traces the behavior of the scheduler over time. As you can see as from the figure, C ran 5 times, twice, and B just once, exactly the proportion to their ticket values of 250, 150. Lottery scheduling achieved the proportion, proportionally probabilistically over time, and stride scheduling gets them exactly right at the end of each scheduling cycle. So you might be wondering, given the precision of the stride scheduling, why use lottery scheduling at all? Well, lottery scheduling has one nice property that a stride scheduling does not. No global state. Imagine a new job enter at the middle of our striding scheduling example above. What job enters in the middle of our stride scheduling example above? What should its value should be? Should it be set to 0? If so, it will monopolize the CPU. With lottery scheduling, there is no global state per process, and we simply add a new process with whatever tickets it has. Update the single global value to track how many total tickets we have and go from there. In this way, the lottery makes it much easier to incorporate new processes in a sensible manner. Section 9.7. The Linux Completely Fair Scheduler, the CFS. Despite of these earlier works in a fair share scheduling, their current Linux approach achieved similar goals in an alternative manner. The scheduler, entitled the Completely Fair Scheduler, or CFS, The implemented fair share scheduling, but does so in a highly efficient and scalable manner. To achieve its efficiency goals, CFS aims to spend very little time in making the scheduling decisions through both its inherent design and its clever use of data structure well suited to the task. Recent studies have shown the scheduler efficiency is surprisingly important, specifically in a study of the Google data center, Kanev et al. So, show that even after aggressive optimizing, the scheduling uses about 5% of the overall data center CPU time, reducing the overhead as much as possible, and thus a key goal in modern scheduler architecture. So, batch operation. Whereas the most schedulers are based on around the concept of fixed time slices, CFS operates a little differently. Its goal is simple: the fairly divided CPU evenly among all competing processes. It does it through a simple counting-based technique known as virtual time, VRun time. As each process run is accumulated VRun time in most basic case, each process with runtime increases the time same rate. In proportion with the physical real time, when a scheduling decision occurs, CFS will pick the process with the lowest VRun time to run next. This raises questions: how does the scheduler know when to stop the currently running process and run the next one? The tension here is clear. If the CFS switches too often, fairness is increased, as the CFS will ensure that each process receives its share of the CPU even over minuscule time windows, but at cost of performance too much context switching. If the CFS switches less often, the performance is increased, reduced context switching, so at the cost of the near-term fairness. CFS manages its tension through the various control parameters. The first is the schedule latencies. CFS uses this value to determine how long the one process should run before considering a switch, effectively determining its time slice, but in dynamic fashion. A typical scheduled latency value is 48 milliseconds, so CFS has divided this value by the number of the processes running on the CPU to determine the time for slices for a process, and thus they ensure that over this period of time, CFS will be completely fair. For example, if there is n equals 4 processes running, CFS divided the value of the schedule underscore latency and by the n and arrived at a per process time slice of 12 milliseconds. CFS then scheduled the first job and landed until and it has used 12 milliseconds virtual time and checked if there is a job with a lower VRun time to run instead. In this case, there is a CFS would switch to the one of three other jobs and so forth. Figure 9.4 shows an example where the four jobs A, B, C, D and each run for the two times slices in this fashion. Two of them, the C and D, and completely leaving the just two remaining, which run of the 20 milliseconds in round-robin fashion. But what if there are too many processes running? Wouldn't that lead to a smaller time slice and thus so many context switches? Good questions, and the answer is yes. To address this issue, CFS added another parameter, mean granularity, which is usually set to the value like 6 milliseconds. CF will never set the time slice of a process less than this value, ensuring that not too much time is spent in scheduling overhead. For example, if there are 10 processes running, our original calculating would divide the schedule underscore latency by 10 as to determine in order to determine the time slices reached 4.8 milliseconds. However, because of the mean granularity, CFS will set the time slice of each process to 6 milliseconds instead. Although CFS won't quite be perfectly fair over the target scheduling latency, schedule under latency of the 48 milliseconds. It will be close to n, will achieving the highest CPU efficiency. Now, note that the CFS utilizes periodic timer interrupt, which means it can only make decisions at fixed time intervals. This interrupt goes off frequently, for example, every 1 millisecond, giving a CFS a chance to wake up the determining if the current has reached the end of each run. If a job has slices that is not a perfect multiple of a timer interrupt interval, that is okay. CFS tracked VRAM time precisely when it means that over the long time hold, it will be eventually approximated the idea of the sharing of the CPU. Weightings, niceness, weighting. The CFO also enables control over the process priority, enabling users or administrators to give the processes a higher share of the CPU. It does not with the ticket, but through a classic Unix mechanism known as a nice level of the process. The nice parameters can be set anywhere from the 922 plus the 1940 process. With a default of 0, positive nice value implies lower priority and negative values imply the higher priority, where you iterate too nice and you just don't get as much scheduling or attention alas. The CFM maps the nice values of its process to weight and as shown here. This weight allows us to compute the effective time the slice of each process as we did before, but now accounting for their priority differences. The formula used to do so as follows, assuming the n processes. Let's do an example to see how this works. Assume there are two jobs, A and B, and A, because each our most precise job, and is given a higher priority by assigning each nice value of the 5 minus 5. B, because it hits just the default priority, nice value equals 0. This means weight A from the table is 3121, where the weight B is 1024. If we then compute the time slice of each job, you'll find that A's job slice is 3/4 of the scheduled underscore the latency, hence 36 milliseconds, and B's about 1/4, hence 12 milliseconds. In addition to generalizing the time slice calculation, the way the CFS calculates VRAM must also be adapted. Here is a new formula which takes the actual runtime the process I has accurate runtime I and scaled it inversely by the weight of the process by dividing the default weight of the 1024 weight 0 by its weight and weight. In our running example, A's runtime will accumulate 1/3 of the rate of the bits. V runtime I equals V runtime I plus weight 0 over weight I is runtime I. One smart aspect of the construction of the table of the weights above is that a table preserves the CPU proportional ratio when the difference in the nice value is constant. For example, if the process A instead of had a nice value of the 5, not 9 minus 5, and the process B had a nice value of 10, not 0, CFS would schedule them in exactly the same manner as before. Run through the math yourself to see why. Next section is using red-black tree. One major focus on CFS efficiency, as stated above, a scheduler there are many facets of the efficiency, but one of them as simple as this: when the scheduler has to find a next job to run, it should do so as quickly as possible. Simple data structures like lists don't scale. Modern systems sometimes comprise of 10,000s of the processes, and thus searching through a long list every so many multi-seconds is wasteful. CFS addresses this by keeping the processes in a red-black tree. So red-black tree is one of the many types of the balanced tree, in contrast to a simple binary tree, which can regenerate to dislike the performance under worst-case insertion patterns. Balanced trees do a simple extra work to maintain the low left depth and thus they ensure that operations are logarithm, not linear, in time. So CFS does not keep a process in this structure, rather only learning alone of a process as a captive bearing. If a process goes to sleep, say waiting to an IO to complete or a few network packets to arrive, it is removed from the trace and kept track of where elsewhere. Let's look at the example to make this more clear. Assume there are 10 jobs and they have the following values of winner time: 1, 5, 9, 10, 14, 18, 17, 21, 22, and 24. If we kept these jobs in ordered list, finding the next job to run would be a simple, just remove the first element. However, the figure 9.5 CFS block tree, when placing the job back into the list in order, we would have to scan the listing and looking for the right spot to insert it and order an operation. Any search is also quite inefficient too, and also taking linear time on average. Keeping the same values in red block trees makes both operation more efficient and as depicted in figure 9.5, processes are ordered in trees in real time, and most operations such as insertions and deletion are logarithmic time and I, that is, O log n. When n is the thousand, the logarithm is noticeably more efficient than linear. Dealing with I/O and sleeping processes. One problem with picking the lowest long time to run next rise with jobs that has gone to the sleep for a long period of time. Imagine the two processes A and B, and one of which A runs continuously, and the other B, which has gone to the sleep for a long period of time, say 10 seconds. When B wakes up, its real run time will be 10 seconds behind A, and thus, if not careful, B will now monopolize the CPU and the next 10 seconds while it catches up, effectively starving A. CFS handles this case by altering the runtime of the job when it wakes up. Specifically, CFS sets the runtime of the time that job to the minimum value found in the tree. Remember, the tree only contains learning jobs, and in this way the CFS avoided starvation but not without cost. Jobs that are for sleep for short periods of time frequently do not ever get their fair share of the CPU. So other CFS run. CFS run has many other features, too many to discuss at the point it's in the book. It includes numerous heuristics to improve cache performance, has a strategy for handling the multiple CPU effectively, as discussed later in the book, can schedule across large groups of processes instead of treating each process as an independent entity, and many other interesting features. Read recent research starting the Brown to run more. And the tip, the efficient data structure when appropriate. In many cases, the reader will do. In many cases, it will not. Knowing which data structure to use when is more hallmark of the computing engineering. In the case studies discussed herein, simple lists found in the earlier scheduler simply do not work well with the modern system, particularly in the heavily loaded server found in data centers. Such systems contain thousands of active processes searching through a long list to find the next job to run on each core every few milliseconds would waste precise CPU cycles. A better structure was needed, and CFS provided one by adding an excellent implementation of a readable tree. block tree. So more generally, when picking a data structure from a system you are building, carefully consider its access patterns and its frequency of the usage. By understanding these, you will be able to implement the right structure for the task at hand. 9, Section 9.8 Summary. We have introduced the concept of the proportion share scheduling and briefly discussed the three approaches: loaded scheduling, striding scheduling, and the completely fair scheduler CFS of Linux. Loaded uses randomness in a clever way to achieve the proportion share. Stride does it deterministically. CFS's only layer scheduler is discussed in this chapter, and is built like a weighted long robin with the dynamic time slices, but built to scale and perform well under load. To our knowledge, it is most widely used fan share scheduler in existence today. No scheduler is panacea, a fair share scheduler have their fair share of the problem. One issue is that such approaches do not particularly mesh well with I/O. As mentioned above, jobs that perform I/O occasionally may not get their fair share of CPU. Another issue is that they leave often the hard problem of the ticket or priority assignment. That is, how do you know how many tickets your browser should be allocated, or what nice value to set your next editor? Other general purpose of scheduler, such as MLFQ we discussed previously, and other similar Linux scheduler, handle these issues automatically, and these may be more easily deployed. Good news is that there are many domains in which these problems that are a dominant concern and a proportional share schedulers are used to great effect. For example, the virtualized data center or cloud, where you might like to assign 1/4 of your CPU cycles of the Windows VM and the last of your base Linux installation. Proportionally sharing can be simple and effective, and the idea can be expanded to other resources. See the Schwarzberg for further details on how to proportionally share the memory and VMware the EXS server.